Our good friend J Random Troll is holding onto a rope, and this is attached to a 180 kilogram sculpture, which obviously he's stealing. He's going to pull it with a force of 600 newtons at an angle of 30 degrees above the horizontal, and ultimately the sculpture accelerates in the horizontal direction with a magnitude of 1.1 meters per second squared. So we need to figure out what the normal force is on the sculpture and how hard friction is pushing backwards against this motion. Let's do it. Now, because I'm a terrible artist, which you all probably know by now, I'm not going to attempt to draw the sculpture. Instead, I'm just drawing it as a little box here. But you can see the rope. It is at an angle of 30 degrees above the horizontal. So I'm going to draw a free body diagram of the sculpture, and this is going to consist of all the forces acting on it, not any of the forces that the sculpture is exerting on anything else. To do the free body diagram, every force is going to start right at the center of the object, at least for now. It'll get more complicated when we get further in the semester, but this is where we are for now. And let me think about all the forces that are acting on it. Well, we got gravity. That always acts downward, and it always equals the object's mass times the acceleration due to gravity, which is 9.81. So in this case, my mass is 180, g is 9.81, so I can solve for this force at the very least. It's 1765.8 newtons. We also know there's a force from his rope. That's going to be a tension force, and it pulls just directly in line with that rope. So I'm going to label this the force of tension. It has a magnitude of 600 newtons, and it's pointing upward at 30 degrees. Because we're on the ground is also pushing up on the box a little bit. Oh, looks like J-Random's jumping right now. Woo! The ground also pushes up with what's called a normal force. And I don't know its value. That's what I'm going to be solving for. Finally, there's a force of friction that always tries to prevent things from moving. Right now, this box is not only sliding to the right, it's accelerating to the right. So the force of friction is going to be acting to the left. And these are all the forces that are acting on it, so my free body diagram is complete. Awesome. Now I need to figure out what the normal force is and what the force of friction is. So to do that, I'm going to have to look at x and y directions separately, just like every other problem we've dealt with pretty much this whole semester. So I'm going to go back, look at each and every individual force, and find its x and y components. Let's start with gravity. Gravity's pointing straight downward. Oh, by the way, I should probably determine which direction is positive and which is negative for each of these forces. I'm going to consider my upward forces positive, my downward forces negative, rightward positive, leftward negative. So, in the y direction, I've got a force of gravity of 1765.8 newtons, and that's downward. Now, in the x direction, gravity has no force, which you all have a lot of practice with your projectile motion problems. Gravity does not act horizontally. I know I have a normal force, and it's acting upward, and all of it is in the y direction. So I don't know exactly what its value is, but I know that it's a positive upward force. So I'm just going to leave it as a variable right now, Fn. I also know my normal force, since it's only in the y direction, has 0 newtons that way. Here, I should be putting little subscript x's and y's on this just to make it really clear. So Fny is just the full value of Fn. How about that? Now the force of friction is acting only in the x direction, and it's pointing leftward. So I'm going to head over to my chart and include the force of friction in the x direction. Notice that I put a negative in front. That's simply because it's pointing to the left. Also in the y direction, I marked that it is 0 newtons. One more force to go, and that is our tension force. Now this one I'm actually going to have to break into x and y components. Well, I know in the x direction, it's simply going to be the grand total, 600 newtons, times the cosine of 30 degrees. And that comes to about 519.6 newtons, just horizontally. The vertical component of force is going to use sine. And since the sine of 30 degrees is 1/2, that means my y component of tension is just 300 newtons. Awesome. So now I've taken each and every one of my forces and I've broken them into x and y components. Now it's time to take a look at our totals. I know that force equals mass times acceleration in total, but I also know from the problem that all of the acceleration is in the horizontal direction. This means the vertical acceleration is 0 meters per second squared, meaning the box is not speeding up upward or downward, it's just accelerating to the right. So that means in the vertical direction, Fy total, that's going to equal mass times acceleration in the y direction, that's going to equal 0. I know that in the x direction, Fx total is going to equal the mass times the acceleration in the x direction. Well, my mass is 180 kilograms, my acceleration is 1.1, so that comes to 198 newtons. All right, so in total I've got 198 newtons. I'm assuming it's accelerating to the right. I've got 0 newtons in the y direction, so I can set that equal to just the sum of all of these forces, looking at the x and y direction one at a time. So let's start with x. When I add all of these together, I get 0 plus negative force of friction plus 519.6. So my grand total is 519.6 newtons minus the force of friction. And I know my grand total is also mass times acceleration in the x direction. And that came to 198. So I can set the sum of each of my individual x forces equal to 198. Now I can just add the force of friction over to the other side, subtract the 198, and I end up with the force of friction being 519.6 minus 198. And that means friction is acting with a force of 321.6 newtons. Nice. I can do the same thing in the y direction to get my normal force. When I add them all together, I get 300 plus the normal force minus 1765.8. And that'll all equal mass times acceleration in the y direction, which as I previously said is 0 newtons. So now I'm just going to solve for my normal force, and ultimately that comes to 1465.8 newtons. Fantastic. Right. So that's how you use free body diagrams and forces to figure out a little bit about what's going on in a given situation. We'll practice this some more in class.